Well, students, here we go. It's another screencast with Mr. Swan. Today is going to be the Friday lesson for March 27th, and we're going to be talking about global warming. We'll do a little bit on the notes. I have some graphs for you to look at, a sheet for you to work on. There's a simulation for you to play around with if you'd like. And then I have a how's it going form for you to fill out at the end, because this is the end of week 2. Who would have thought that online school would have gone this long? But here we are. So, picture of the day. What does the Milky Way look like? Short answer, nobody knows. Long answer, we're trying to get a good idea. The bar and spiral structure legacy group is a group of people who are trying to figure out what the Milky Way actually looks like. We do not really have a great picture of it because we can't really get outside of it. If you remember all the way back in the beginning of the year, there was that structure that I showed you in the Unit 1 notes, and then we thought it had like 2 arms coming off of it. So we called it a barred spiral galaxy. And now, based on the research of this group, they think that there's now more arms. So this picture that's on the left is what they believe that the Milky Way galaxy actually looks like. And this might actually update the picture of my slides, which I think is always a pretty neat thing. And we are going to be located about halfway from the center, which is what they thought before. And we would be located in this picture on the left, right here, where my cursor is. So this arm, which is called the Perseus arm, there has like a little bit of a branch. So it comes out and it comes out over here and it branches off. We're like about halfway in the middle of that branch. Is what what they believe, at least. They can't really take great pictures of it, but you can get some microwave data. You can also get some radio wave data, and they're using those to try to figure out how this is actually working. So how many hours did it take? They have spent about 5,000 hours collecting data of the different parts of the Milky Way from different directions as we orbit around the sun. And this is the goal, to try to make some kind of map of what they believe it actually is. So right now there's some good support that this is the new updated version. On the right side is a diagram kind of showing what the different names of the arms would be, where the different clusters of planets are that we kind of go through, and those are all color coded for you to kind of take a look at on the right as well. So a pretty neat article that came out, which was kind of a surprise to see someone was like, hey, this is what the Milky Way looks like now, and not what we actually kind of believed it to be before, which is always a fun time. Continuing right on, going for the notes today, just a tinge of review from yesterday. Specific heat, latent heat. Specific heat is the amount of energy needed when a substance goes up a degree in temperature of the same phase, right? So when water goes from 30 degrees to 31, then to 32, and so on, degrees Celsius. And latent heat is the amount of heat needed when you're changing phase of a substance. So when you want ice to go to liquid water, or you want liquid water to go to a gas, or you want to take something that's like a solid metal and you want it to melt it to go into like that liquid type of metal. So those are the two. They're going to come on up again today and kind of continuing out through the rest of the unit. So just a tinge review on that. And now we move on to really the big thing, which is radiative cooling. And this really is the most simplified diagram of global warming that there could be. Is that we have energy coming from the sun, and that energy gives us light, it gives us heat, and then something has to absorb that heat. Some of it gets reflected immediately, like let's say you had maybe some clouds right here, they can bounce some of that light back up into the atmosphere. If there is ice, that's really, really good at reflecting, so they can bounce some light back up into the atmosphere and out of our planet as well. Or it gets absorbed, which would be something that's usually a little bit darker, a little bit rougher. Ocean can absorb pretty well, land can absorb pretty well. And when it absorbs that light changes. And from our electromagnetic spectrum, we know that there's 7 different types. Invisible light is one of them. And the one that it changes to will be a longer wavelength. So it goes usually from shorter wavelengths to longer wavelengths. In this case, it goes from visible light to long wave infrared, which is a very fancy way of saying heat. It's the same idea in your bedroom. If you have your light on, and then you go over to like the wall and you turn the light off, the light disappears. But it doesn't truly disappear. You just can't see it anymore because it has changed. And what happened is that when you turned off that light, the bulb which was shining out, the shorter wavelength comparatively of visible light. Those wavelengths go across, they eventually hit like the wall, and then the wall absorbs it and changes it into heat energy. How much heat energy is it? Well, not a lot. Extremely tiny bits. Now, but if you take that light bulb and make it the size of the sun and as hot as the sun, well, then you can get a lot more energy, which means you can get a lot more heat. Is this a good thing? Is this a bad thing? Well, this is a great thing, because if that didn't happen, then we would not be able to survive. We need heat. And so we need our ground and our planet to absorb it and to let it go back as longer wave infrared. So it does a lot more absorbing during the daytime. It does a lot more radiating out of that heat at nighttime. But it can also happen during the day as well. And we need that. Now, the big issue would be that if you absorbed it all during the daytime and then it all goes out at the nighttime, then that nights can get pretty cold pretty quickly. So really what you need after that is some kind of barrier up here to trap in like a little bit of heat energy and then kind of send that back down. This is the same method and same idea as that when you go outside and it's really cold, your body is radiating out heat energy, but you need to keep some of that in, so you put on a jacket. That jacket is that layer of whatever that substance is in that jacket, right? It could be like a down jacket or like some kind of like fancier foam or some type of like a felt, like a plastic, kind of like in there, right? And it absorbs that heat and then it radiates it back, which is good because then you keep warm. So really your body is what keeps yourself warm in essence. The jacket just kind of helps it. It helps kind of prevent a lot of heat energy from escaping very quickly. So a really warm jacket, in essence, the jacket doesn't give heat at all. What the really warm jacket would be a jacket with just a whole bunch of insulation that helps to kind of prevent that heat from escaping. And so what we call this the greenhouse effect, which is probably something I believe you have heard before from back in middle and elementary school. And is this a good thing? Is this a bad thing? Well, this is a great thing, because without that greenhouse effect, we would not be able to hold heat in our planet, and it would become pretty bad pretty quickly. During the daytime, it would be scorching hot, and during the nighttime, it would be extremely cold. And there are planets we have found that fluctuate like that as it rotates into the daylight and outside of the daylight from our Earth, or from the sun. What we need is some kind of boundary, and that's pretty much what the greenhouse effect actually would be. So this slide, the Earth's atmosphere will absorb some of that thermal radiation that's emitted from the Earth's surface. As that heat energy comes out, it goes into our blanket, in quotations in this part. That blanket is gases. The number one gas that holds in heat for us as a ginormous amount, like which gas is it that holds all the heat and gives it back to us in the most total amount of heat, is actually water vapor. So water is, as we know, it's pretty good at holding in heat, and it's pretty good at letting it out, or I guess we could say pretty bad at letting it out, depending on how you view it, if you want it to come out fast or you want it to come out slow. But it's pretty slow at kind of letting it out. And it does let it, though, out when it condensates and lets out hot air eventually to the atmosphere. So these gases like hold the heat in for us. And how this works, and this is a little hard for me to draw, but that heat energy radiates out from the Earth, and then it hits a gas, and then that gas absorbs that heat energy and then lets it out in a completely randomized direction, which is kind of a neat part about that. We have no idea exactly how to predict exactly where it is, but if you use statistics and math, then you know almost exactly the amount that it comes out. So determining if that individual particle will let that heat out, in the direction of space or direction of the Earth, you can't tell. But if you did it as a whole amount and averaged it out, then you actually can work it out, and then you can actually be able to tell. So this is how we actually kind of get a lot of that data. So it's a lot of math, a lot of statistics. So what is carbon dioxide? Carbon dioxide holds heat better than water vapor does. Roughly about 4 times or so better. There are other gases that are even better at holding heat than carbon dioxide, like methane. Methane does it like 10 times better. So this is the big issue about carbon dioxide, is that you don't need as much carbon dioxide in the air as water vapor to eventually hold in a lot of heat. Even just a little bit of carbon dioxide will it can add up, and you start to hold in a crazy amount of heat from that. So the gases carbon dioxide and water vapor will absorb infrared energy, then re-emit them back to Earth, keeping the Earth warm enough to support life. Again, does it all get emitted back? No, some of it gets emitted towards the direction of space, and then it kind of goes. But that's how it kind of goes. So if you've ever been into a greenhouse, which I'm assuming sooner or later you probably have been into one, greenhouses are really good because it lets in light, right? Shortwave. So that shortwave can work its way through the glass, and then it gets absorbed in there. And then when it tries to radiate out that heat energy, it's a lot easier to grab onto longer wave energy. So that glass will actually hold on to that heat better. And then it absorbs that, then it radiates some of it back in the direction of the greenhouse or whatever inside the greenhouse. And that's how they keep warm over time. So that's how a greenhouse works, that the glass lets in shortwave and then keeps and holds on to long wave a little bit better. What is the global warming issue, though, is how thick the glass is in this case. That if you have a greenhouse and everything's going pretty well, in essence, you want to keep it that way. So you want the glass to pretty much be the same, right? That you want the amount of heat energy being stored to be constant. And the more constant it is, the better life can flourish. If you start changing it in some way, like if you were like, say, 1 month, take out all the glass, then everything inside is going to have a big problem. If you do the opposite, you're like, hey, next month I'm going to like triple the thickness of the glass. Then everything inside is going to have a problem as well, just the opposite direction. Instead of being too cold, it could get too warm. This is the big issue for us. And so you might think that I would have like lots of slides for climate change and global warming, but I don't. I really just have the one because global warming is a tinge of I don't want to say misnomer. But even the person that coined the term has tried to like switch it to more or less a climate change kind of term, because some places will get a little colder. And some places will actually get a little more precipitation. And some places will just get hotter. And it kind of depends on the location. So throughout the year, I've kind of brought this up, and I try to put a little bit of it into each unit of, what does global warming mean? And in my opinion, truly, is that it changes based on where you are. In New York, in Burnt Hills, we are not probably very concerned with rising ocean. Like, I'm not worried I'm going to lose my house because the ocean level is getting higher, because we're at such a higher elevation here that even if all the ice melts in the entire world, that ocean sea level can never rise up to where we are right here. So in that regard, it'd be like, okay, well, that's fine. Are there other issues? For sure. And we'll kind of go right through all of those. And this depends on where you live. If you live on some of those island nations over in the Pacific that are about, some range from just a few inches above sea level to, maybe just a few feet above sea level, a rise in sea level of a few feet becomes their biggest concern. So it just depends on what's going on in your area and what global warming is going to do to that. So this also brings up a good point that there was an article. It was, in essence, it was more of an open letter that is written to pretty much like all science teachers. It was about criticizing the way that they teach global warming and climate change. And it came down to that science teachers are sugarcoating it for the students, that they don't want the students to feel bad. So they're trying to like add in like a little bit of hope into some of these things, and maybe not being as 100% honest about it as they could be, in essence, because they don't want the teachers to feel bad. And I'm going to be honest, that I was like, that maybe is me, just a tinge. So they wrote down exactly pretty much the sentence that it should be, and that you should tell your students. And I'm going to tell you what it is right now. Are you ready? Good, because here we go. Humans are increasing the greenhouse effect by adding more CO2 in the atmosphere, so more infrared waves are being trapped, emitted back to the Earth. It is 100% caused by humans. The problem is going to get very, very bad. It probably can't be reversed at this rate. That's what they wanted us to say. Is that is it 100% caused by humans? Yes, it is caused by humans. I'll explain how we actually did this before. Is it going to get better? In the short term, probably no. And I say probably, I'm like practically 100% no. In the long term, can it get better? Yeah. Will we live to see it? Us personally, probably not. Could your kids, maybe grandkids, live to see it? Possibly yes. See, like that's me sugarcoating it right there. I just can't help it. That's just the kind of guy that I am. But we're going to go into what did we do to cause this, and we really did something that no other animal has ever done before, and it's quite impressive, to be honest. So I'm going to come back to the consequences in just a little bit, and I'm just going to jump right ahead to this one, the carbon cycle. This is what it goes to. Carbon goes up in our atmosphere, carbon dioxide, all the time. We breathe it out. Animals do all over the entire world. It's a cycle, right? And then as we breathe out that carbon dioxide, other things like plants take it in, right? Through photosynthesis, because plants want the carbon. They do not want the oxygen, right? So then they spew out the oxygen, which then we breathe in that oxygen, and then we breathe out that carbon dioxide. So we have this kind of nice thing going where plants take in the carbon and we breathe out the carbon. So there's always, that carbon cycle was there. And humans have not always been around. So that carbon cycle has been going on long before humans have been here. And that's an important note to take up. And carbon continues around. And eventually things over time, they can die. And then when they die, they can decompose and you have more carbon goes up into the air. But then also like different types of bacteria will start to take that carbon. Again, plants and stuff will start to pull in that carbon. Some carbon actually eventually goes into the ocean. The ocean is a fantastic sink. Sometimes they call these two things source and sink. Source means where something comes from. Sink means where it's going to. The ocean is a ginormous sink of carbon. It pulls it in. And then it eventually, sometimes that carbon can eventually goes and be used for the phytoplankton in the ocean for photosynthesis. The animals can like use it down in the ocean, and eventually some of it can actually get stored down there. And some of that carbon actually gets spewed right back out of the ocean as well. And this has been going around for a very long time. This has been pretty much where our carbon cycle is. So it eventually goes into gas in the atmosphere. Plants pull it down as a solid. Eventually it can decompose. It can go into like liquid, and then eventually get back to gas form. It eventually goes maybe up in the air again. It eventually goes back down into the ocean. And eventually, now it's back into like the liquid form. Eventually works its way back out as a gas. So it can be as a solid back down in the ocean, depending on how deep it goes. And it goes around and around and around. What we have done is we have done something very special. Is that a long time ago, now we're talking like millions of years ago. We talk about the history of the Earth. We'll go into this a lot more, but in short, a very, very long time ago, the king of the plants, which is the tree, takes in a whole bunch of carbon throughout its lifetime. And then eventually the tree dies. Tree falls down, and then today the tree decomposes. If you went back millions of years ago, the trees exactly did not 100% decompose like they do today. There was no organism to do that. It didn't evolve yet. And the one that it is like a nickname. It's like me, a fun guy. Truly, the fungus. It goes around and it decomposes, decaying matter. That was not evolved when the wood type of trees started to evolve, which looked a little bit different than what we had today. Is that they would grow and they eventually get really big and they would die and they would drop down the ground, and then there they would stay. And depending on the type of ground that they kind of dropped into, they can drop into like water, right? Because waters are really good at not letting things weather. And then eventually, we talk about like our rock unit, things going to get buried. And if they get buried, they don't really get weathered very much way either. And so then they would stay, and then you had all this organic matter just kind of laying down on the ground, plant organic matter. And, in swamps and eventually in lakes, and eventually it would get buried by sediment, and eventually it would get buried. And eventually, if you take a whole bunch of carbon and you bury it in the ground and you add heat and you add pressure to it, this is going back to our rock unit, it eventually turns into coal, oil, natural gas. And that's pretty much what eventually starts to form, like right down here in the earth. So what happened is a very long time ago, our planet was very, very hot, way hotter than it is today. Like New York State would be like kind of like a Florida-y tropical region, even at our latitude. Based on like how much carbon dioxide was actually in the air at that time. Plants and trees took it all out. They eventually helped us bury it. And so they buried a crazy amount down there. And when doing so, reduced the amount of carbon dioxide in the air, which then reduced the heat. which has been amazing for us. And so all that carbon in the air, which would make our world probably too hot for us, has now been buried underground as a solid, as a liquid. And there it has stayed. And the big change that humans have done is that we have figured out how to go down really deep into the earth and drill it up. And then we take it up to the surface, and then we use it. And the way we use it is, nutshelling this, we set it on fire. We take the solid form and the liquid form, and we set it on fire. We change that form into a gas. And so then we add that gas back up into the atmosphere. And that's what global warming is. It is because we're adding that carbon dioxide up. There's nothing taking it back as a gas back down as a solid, or eventually even into a liquid. Because the plants that are already doing it have pretty much are already here. It's a lot harder to add more plants to the land that we already have. Like, it's in essence saturated. You can try to like make more forests and things like that, and that will reduce it just like a little bit, but not into the amount that we're pumping it up. And the amount that we pump it up into the atmosphere is more and more every single year. In your lifetime, you have seen about a 15-year-old student or so, roughly about 20% of all carbon that has ever been used and put up in the atmosphere has happened in your lifetime. Me, I am like in my mid-30s. I have seen, based on this graph I looked at, about 40% of all carbon has been pumped up in my lifetime. So this is more of a recent issue than a long time issue. Even though the Industrial Revolution happened hundreds of years ago, the speed at which we're moving it up in the atmosphere has only really picked up, and I'm going to say, in the most recent modern times. This is why it's becoming such a concern, especially right now. So no animal has ever done that. No animal has ever been able to dig down into the ground miles, on land and into the ocean, find these sources of carbon, and then set it on fire. It just hasn't happened. So we're the only ones who have done that. And we do quite a bit. Now, the other kind of interesting fact is that if you take all the carbon that has ever been used and burnt, from oil and coal and all those sources, and you kind of imagine the entire amount for like humans have ever used, right? That compared to what is buried down in the ground is, no joke, like a drop in like a 5-gallon bucket. The amount down there is an absurd amount of coal and oil down there. The problem is for us is that we can't get to it. It's too deep. So when we talk about like coal running out and oil running out, that's not 100% true. What they really mean is easy access to coal, easy access to oil, because you can only drill down so deep before eventually the drills can't go anymore. That's why pretty much on land, you don't really see too many of those oil wells anymore, right? They've all moved them offshore because anything that was on land that could be of God they've already pretty much taken. So that's why they're moving into the ocean, and that's why they move further and further into the ocean every single year. That's why when you go to the beach, you probably all over the United States, you guys have been to beaches all over the place, you probably have never seen an oil platform, that they're too far off in the distance, and they have to constantly go back every single year because they eventually will pull it up. So that's another reason why this is like a little bit of a concern. It's, to a degree, it's getting harder to get. And then the climate consequences are being harder to get as well. Now, if somehow we invent a solution or a process or a machine that can take carbon dioxide as a gas and then make it back into a solid or liquid again, global warming's done. It's over. Just like that today. That process, as of 3 years ago, was not invented. They have actually now invented one. But the amount of machinery they need to bring down the levels, based on how big those machines are, based on the amount that we're pumping up into the air, would be about 4 times the size of Manhattan. That's a lot. That would be like a very, very big factory. But on the other hand, it's a little bit of hope that, that's the method today, but maybe that can be improved upon in the future. So like, maybe making those more efficient. And then there's a big push to go for green energy, right? So instead of, trying to get electricity from, burning like coal and oil, right? What if you use solar panels? Because then you would reduce the amount that you actually need to pull up and burn, which would make sense. And if you change your car to electric, you would reduce the amount that you would need to burn. A lot of shipping container vessels, which are ginormous, which carry all those cargo ships, or that cargo eventually to us, and they travel all across the world. They pump out a ton of fossil fuels, and they use a ton to ship that stuff right around the world. No joke. One of those vessels trips is like pretty much all the cars on America on the road at once. So like if everybody had a green car today, that helps, but like other things have to be changed as well. So one of the biggest groups that owns not most, but a very large amount of those cargo ships from Europe just recently announced that they're planning to, and they believe that they can go entirely 100% green by the year 2050. That's what their goal is, to change those ships over. And that eventually, there's like a little bit of an economic boost. They're like, well, if it's cheaper to get energy from, maybe renewable energy than it is from digging it up, well, then that pushes more people to kind of want to go get the cheaper energy. So there's people who are working in economics on this. Scientists are working on this. Business people are working on this. Right? So it's going to be a great group effort. Right? So if people are using global electricity in their homes or making homes more energy efficient, well, then less needs to be burned. If we add up some spinning turbines, or like I want to use the word windmill, but I know that is not technically correct. For like that captures like the air, right? For wind power, that would reduce the amount they need to pull up and burn. So there's a lot of places that are kind of working on these. And these ideas, and it won't really in my opinion, there won't be one breakthrough idea that changes this completely. This will be the summation of thousands and thousands and thousands of groups and people and combinations of ideas that eventually kind of work their way on down to eventually to where we get to our reasonable level. So do I think it can happen? Yes. Is it too late for us? This becomes a little bit more of an issue. If you stop all new carbon entering the atmosphere today, the amount of time it would take for that actual carbon that we pumped up to diffuse out is pushing about 100 years. So the benefits that we do today, we will not enjoy in the future, but your children will. And your grandchildren will. And that's pretty much where a lot of this is coming from too, is that we constantly make the world a little bit better. And there's also some other side benefits to this. If you have less factories that are burning this type of fuel, well, then your air gets a little bit cleaner. If you have airplanes that switch over to green instead of burning fuel, then you actually will have more sunny days and less cloudy days, which is a neat little byproduct. So which in theory, over time, that also means less pollutants in the air, which then could actually reduce the rates of asthma. So there's like a lot of good reasons to kind of work on some of this stuff, and that's why I think a lot of people are kind of going for it. Some companies that have like benefits and subsidies from the government those have been taken away. Sometimes they come, sometimes they go, and that's okay. But they're still doing it anyways because they still think they're like, people kind of want this, and my employees kind of want this, and representatives kind of want this, and then that's what's kind of working with this. So if you want to make a difference, one of the best ways is to vote. The best way to reduce carbon actually in your lifetime is actually vote your representative and say like, hey, this is something that I kind of care about, and you're my representative, and I believe you should then care about it too. And you can write them a letter, and that's kind of a big deal. They don't actually get too many letters, believe it or not. And so that's what they're kind of wondering where their constituents go. So that's becoming more of like a political issue as well. And you'll see that as time goes on. And you guys are very, very close to voting age. So you'll see that even more. So that's, in essence, in a nutshell, what global warming is. And if we could stop the burning, then it ends today. Can we stop the burning? Not really. People need transportation. So we need alternatives. People use a lot of plastic. Plastic comes from oil. So we need alternatives. This is like a little bit of the plastic ban, is that in theory, you're actually not having people buy plastic bags at the store or getting plastic bags at the store, which then reduces the need for plastic bags, which then reduces the burning of and the use of oil for them. So it's just like one of these things that kind of work out. And there's a lot of issues with that too. Like these topics can get quite complicated. If you have any questions though, feel free to email me about them. And we'll talk about it. Because like, what if you stop using plastic but you use the paper bag? And you're like, okay, well, if the paper bag comes from like a forest and you got to cut down the tree and you got to get the pulp to make the paper, and then you have to ship it by using a truck that uses and burns the fuel, how much are you really saving? If you buy a reusable bag, the amount of times that you need to use that reusable bag, it depends on the bag, but it pushes about 25-ish at the best that I've read times before it eventually becomes less environmental impact than that little tiny thin plastic bag. But on the other hand, if you use one and then you use it for years, well then, yeah, it actually did have a net benefit. So these are the kind of things that people kind of talk about and they kind of work out. It's complicated, but that's what we do because we need something to do. Otherwise, what would we do all day? And then so that kind of goes back in here. So what are the consequences? Things that will happen for sure. Sea level will rise. Some cities are already getting hit by this. Miami is already getting hit by this. On a high tide, that tide is already working its way into parts of the city. They have pumps going all the time. We talked about this before, but New York City has pumps in the subway going 24 hours a day, 7 days a week. And my biggest complaint for a dystopia zombie movie in New York City or something like that is that the subways are always empty. But that's not true. If electricity stops in New York City, the subways would fill up with water in about a day. So that's an issue. For us in New York State, in our location particularly, we're estimated to get about 15% more precipitation than we usually do, which is going to be a big issue for farmers, depending on what types of foods that they plant. Certain types of apples, and New York State's known for their apples, do not grow. I take it back. They grow good with a certain amount of water, but if you give them too much water, then it doesn't really make them grow as well. So some farmers are actually starting to prepare for that. This is becoming a little bit of an issue more out in the Midwest, which is they're thinking that they might getting less rain in some parts. And they already go through areas of drought. So there's different companies trying to make more drought-resistant crops, and having more densely packed corn per acre than you can normally plant. So there are entire colleges devoted to the agricultural studies where they try to grow food with less. And it's quite neat to kind of read those articles because one of them is like, is it possible to grow lettuce with 90% less water than we use? And sometimes those answers are no, and sometimes those answers are like, we actually did have some success. And so then that becomes good for everybody because then the farmer can grow more without having, less water, which means less expense, which means they make more money. And then that also then helps us because then if you're using less resources, then that just helps the world as a better place overall. So overall temperatures will go up. What does that mean on average? You will see, last article I read about this, that in my lifetime, there's been about, in New York State, at this location, about 2 more 90-degree days per year than normal. So is it livable? Yes. Is it enjoyable? I'm not really a big fan of 90 degrees personally, but that's just kind of goes. More heat in the air means the sea ice is starting to melt, and land ice is starting to melt. So there's glacier national parks out west. If you want to see them with really cool glaciers, in all fairness, the sooner you go, the better, because every year those glaciers get smaller and smaller and smaller. And they will continue to do so. I mean, some years you can actually have like a little more snow, so they might grow just like a tinge. But then overall, for like the 5-year, 10-year range, that they're getting smaller, and eventually they will go. So if you want to see them now, is always the best time. Same thing with it's gonna be the same thing with some coral reefs. When we talk about ocean, is ginormous carbon dioxide sink. And it takes in a ton of carbon dioxide for us, a very large percentage. The byproduct of that is that when you add carbon dioxide to the oceans get more acidic. So the more acidic the ocean water gets, the harder it is for sea life to survive. In particular, the coral reefs. The coral reefs will have a hard time surviving. So a lot of coral reefs are actually starting to die. So if you went to the Great Barrier Reef over in Australia, it's going. More and more of it dies every single year. So it's like, what's the best time to go visit it? Sooner rather than later. And definitely within the next 15 years, if you want to see it, like at least with some kind of glory. Does that mean all coral reefs are going to die? No. It just means that ones that have been established can't move. They can't really kind of go, so the bacteria inside can't really deal with that kind of acid levels, which then reduces the amount of photosynthesis they can do, which then reduces their amount of energy they get, which means then they die. So that's going to be a big issue. Sea level is going to rise, and it rises every year. It's like half centimeter to centimeter, depending on the place. So that's going on up. Is that going to be a big issue for us? Where we're like 400 feet above sea level? No. Is that a big issue for New York City? Yeah, it's going to be a big issue for them. Any kind of coastal property is going to be a bigger issue. You're having, so that's going to be a little bit more of a problem. If you add more carbon dioxide to the air, you're adding more, in theory, ability to trap heat. And heat is energy. So if you add more energy to the atmosphere, you're going to get more extremes of something. So some days you're going to have more extreme, like plus heat, like you're going to get more extreme droughts and storms. But that can also happen during the winter. You'll still have a winter. So you can have more extreme snowstorms. But you can also have more extreme windstorms. You can have, so it means more extreme of everything. So you're going to see more extreme on both sides of that pendulum swing. This is happening to Lake Erie and all the Great Lakes, is that the winds are getting stronger, which is causing more coastal erosion. So they're having ginormous coastal erosion issues there than they ever had before. It's generating waves from the Great Lakes, which is hitting the land, which is then eroding it away, which is becoming a big issue because once it's gone, you can't really replace it very easily. And it's very, very hard to stop because the Great Lakes are ginormous. So, on a lower level, if you're having like a river, bend and it hits the outside bend and it's causing more erosion just on a little outside bend, we can put up some like stone and some barricades that kind of like reduce that rate of erosion. But that's like a tiny amount of square feet compared to how much coastal and shoreline land there is for the Great Lakes and how much coastal line there is for the entire United States. So that's going to be a big issue. Flooding will be becoming more of a big issue as well. And that doesn't have to be just on the coast. That can happen more inland. So here, not really too much flooding, but if you actually go south New York, like Binghamton Range or the Susquehanna or anything down by the Hudson River, like lower Hudson River, from the last hurricane they had massive flooding. People down there do not fool around with flooding anymore. If there's a hurricane warning, there will be like runs on the gas station where all the gas stations will just be run dry because people down there for that last hurricane, with the flooding they got, some went without power for weeks. That's a very, very long time. And they always usually hit at a bad time, so when it's cold or something like that. So that becomes a really big issue. Change of global weather patterns. Different areas require different climates to grow these different types of food. Some areas will have to change, and they'll have to either grow different types of food or they'll different types of products. And that's much easier said than done. When I talked about like my apple farmers, certain apple species do not grow great with the amount of water we're predicted to get. To rip out those trees, which take 20 years to grow to get there to begin with, is a big ask for a farmer and a very, very risky bet as well. Because, what if you get more? What if you get less? If one of those predictions are wrong, which also becomes a big issue. So, changing like, hey, one year I'm going to farm corn and next year I'm going to do like a soybean. Much easier done than to rip up like, areas where like a vineyard. Be like, hey, grapes don't really grow well here anymore. And be like, well, that's a big issue. That would become a really big issue in France. Remember, their country, comparatively to ours, is much smaller. They have a certain amount of area of land that can do vineyards very, very well. And that's, wine is like a pretty major export of theirs. And some areas are starting to get hit by more water and some areas are getting hit by less water. And grapes are very attuned to that. So if they get too less, they don't taste very good. And if they get too much, oddly enough, they don't taste very good either. So they need just the right amount to make wine. And the grapes that are not good, they sell in the supermarket, which I think is always a funny idea because the grapes that you buy, like I always really like, but those are like the grapes that are not good enough for wine, which I always thought was really funny. So that's going to become like a big issue for them. And then stronger storms, which I talked about. In your lifetime, in just the past year, you saw the strongest, most extended Category 5 hurricane of all time. And we lucked out. It did not hit us, but it easily could have. That will become a big issue in the future. So like, what can we do? And in the short term, there are a lot of people who are trying to make ideas of, what can we do to cool down the world today? Could we, these are all true actual ideas. These are things people have tried on the small scale and are in essence are looking for permission to try on the large scale. Could we go up in the atmosphere and flood the upper atmosphere with a whole bunch of particulate matter, like broken pieces of like micro glass and micro like reflective pieces of metals? Because that would reflect a lot of heat energy back out up into space. Does it work? Yes. Is it also probably going to be a problem when you flood the air with micro pieces of glass and micro pieces of metallics? Probably yes, because people will breathe that in. Another one is like, oceans can take in a lot of carbon. What if it's hard to grow more plants on land because like if you look around outside, it's already filled up. But could we grow more plants in the ocean? There's oceans, there's lots of space, there's a lot of plankton, there's lots of room. What if we flood the ocean with iron, which is like a bottleneck, and nitrogen, which is a bottleneck for plankton to actually kind of grow really fast. And then we flood it with them. You just kind of go out with a boat and pour it right in there. And then the bottleneck is removed. So they have all the carbon they need. They have all the sunlight they need. They have all the room that they need. They would grow like crazy. Does it work? Yes. What it also makes is a thing called an algal bloom, which will then create over time an oxygen dead zone, which will kill all the sea life in that area. So that's real. Is it possible to go and paint things white? Yes. The amount of square area, though, you need to paint white is like millions and millions and millions of square miles. There's just not enough things to paint white before that actually works. But that's what people are talking about, like, making the roads white, making roofs white to help reflect some of that heat back on up. So those ideas continue. There's more and more of them. They're all kind of like, I don't call it like mad science ideas, but they all have like a very serious consequence. And you're like, oh, maybe we should not do that. And at the end of the day, like the big thing is that these are all Band-Aid fixes. That it doesn't really solve the problem, is that we're using too much carbon as a solid and liquid and pumping into a gas, so we have no way to pull it out as from a gas back down to a liquid or a solid. So that is what kind of needs to be fixed. A little simulation for you guys to use, which is this one. I'll put the link for it. Exploring climate change, no questions. But taking a look, you can actually kind of play this and kind of gives you an idea. I'm going to pause it real quick and I'll point out some things. The yellow, let me zoom this in for you. The yellow, that's energy being come down as sunlight. Sometimes it hits ice, right? And bounces and reflects right back off. Sometimes it goes into water and then makes that little red dot. That's supposed to be like heat energy just going around the water, going to land. Green is carbon. Carbon can be sunk down as down into the bottom of the ocean as well. This is supposed to be land ice and sea ice. It can melt and you can change things. So you can say like human emissions as a percentage. So if you think in the future will be double what it is today, then that means we're pumping out more carbon dioxide, which in turn will then cause the air to get hotter, which then will make more water vapor, which then will make more clouds, which then can allow some of that sunlight to kind of get bounced back by the cloud and hold in more heat, because clouds actually will hold in more heat for us. And then you can have this kind of go on for quite some time. And you can see like the average temperature over here on the right side, see like what will happen. On the bottom, it gives you a sense of how much carbon's in the atmosphere. And then over in the bottom, you can see like some water vapor in the atmosphere. And these will slowly start to tick up. And they'll get higher and higher and higher and higher. And then as you kind of like to see for like this one, let me just slow it right down. It's getting harder for some of these things to get out. Like it's trapping in more heat. So then the temperature is starting to get a little bit hotter than it once was. And it continues to slowly get hotter over time. So this is a neat thing to kind of see like how extreme this visualization will get. There's no questions. This is kind of a neat thing to play around with today. And then we'll go on over into this one. So this is a sheet I have for you guys to do. These are actual true climate graphs. Like the real deal. This is what NOAA actually uses. This is what is actually presented every single year by the government. I cut and pasted a whole bunch of them to kind of put it right down here for you to see like what they are. They're based on part in year. As you may know, some graphs don't go back in time, like glaciers measurement only goes back into like the 1980s because we just didn't take measurements before then. So this is what we have. So a lot of data kind of goes way back to like 1800s. Some data just does not. It's just what can you do? That's how life kind of goes. So what I'd like you to do, and this choice I guess will be up to you. Take a look at these graphs. There's some on the first page. right? And you can just do the title if you want. Global average sea level, like over time, it's increasing. Heat trapping gases are increasing. Glaciers are decreasing. And I want you to kind of be like, you can go right on the side and just kind of take a mental note of those. And then here's some more graphs on the next page. And there's 5 questions for you to do. Sorry, 6 questions. I'd like you to kind of like pause this video and go give those a try. So am I going to grade this? No, I'm actually going to tell you what the answers are in about, once you unpause the video in just a few seconds. So I'd like you to go give those a try and see, do you come up with the same kind of conclusions as everybody else? And then I'll show you what makes sometimes reporting global warming so impossibly difficult. So this is the time to pause the video. Did you pause it? Okay, pause it. All right, so now you're back. Hopefully you kind of gave those 6 questions a try, and I figured we'd kind of go right through some answers, and we'll see how it goes. Going right on through these. Global average temperature. If you look really closely, you'll notice that it increases. But if you're really keen, you might notice, see how it kind of like flatlines a little up here? Like the rate of increase from here to here is much steeper than it is from there to there. I'm going to zoom in this just a little more. This is what I'm talking about. From here to here, this is a pretty steep increase. From like there to there, it actually technically is increasing, but not nearly as much. That was actually quite interesting. People thought that was the big hope, that global warming was capped, like it was done, like the heat could only go up so high. And then eventually it got there and it can't go up anymore. That's going to become a little bit of an issue. Carbon dioxide continuously goes up. Spring snow cover, so we're getting less and less cover during the snow during the spring. Overall, in general trend is going down. Ocean heat is going up. September Arctic sea ice going down in general. Global average sea level is going up. Heat trapping gases are going up. Glaciers are going down. Sun's energy is in there, and it, as you might notice, it does fluctuate, but very, very little, and is continuing. So generally pretty steady. So here's the questions. Look at the charts on the first page. List the charts that have similar general trends, like increasing over time. And you'll notice that there's a bunch. Heat trapping gases are increasing. Global average sea level is increasing. Ocean heat's increasing. Carbon dioxide is increasing. Global average temperature is kind of increasing. And then here's the issue a scientists have to go through. How do you know which one influences the other one? Which is going to be a very difficult question. So for those ones, I think you're probably going to be pretty good with the first question. Question number 2. There are charts where the years... Here you go. There are charts where the years are not always increasing or decreasing. For example, the annual mean growth rate of CO2 and Mauna Loa on this page, which is this one. So they're talking about the individual year is very up and down. Like some years up, some years down. No, some years up, some years down. Some years up, some years down. And so for those ones, we have to do a longer annual trend, like a decade trend. And by decade, though, the trend is clear that it's in general it's going up. And the new one will actually be over here when those get published. This graph has continually gone up as well. It's now up to about this year. It should be right about here. So this graph needs to be updated as well. So it's a little pushing like 407, I think, or 410, somewhere right about there. So we can't always look at a year-to-year thing. So we have to look at a longer time. And the reason why is because weather's finicky, right? You have some years you might have the El Nino year. That will throw off observations. So you might have the La Nina year, and that will throw up observations. But if we start comparing all the El Nino years, then you might get a trend. But then some El Nino years are stronger than others. So that will kind of throw it off. So doing weather is very, very difficult. When they make these programs and simulations of weather, they actually apply them not to the future, but to the past. So they take the data from like 1980 to 2000, and they try their computer models, and they see if it works out and is correct. Because predicting weather is very, very difficult. But seeing if your model is correct for those 20 years then gives us a lot of hope that, hey, this model then is probably going to be correct for the next 20 years as well. Why do you think the energy output of the sun was included? The sun's energy output does fluctuate. It does go on these cycles, but some cycles are it goes up a little higher, and some cycles goes a little lower. But in general, it's constant enough that we don't really see ginormous trends on this. I'm really nutshelling something here, which is that our elliptical orbit will throw this around, and precession throws this around as well, which is how the Earth's axis wobbles a little bit. But in general, it's still holding pretty steady. So technically, based on actually precession wobble and based on our elliptical orbit, which actually does fluctuate every single year, which is something I've never really brought up, but I guess I can right now. Sometimes it's not always as constant as what we actually have in the reference table. Those numbers do change, but on very long time scales. We're actually should be in a slight year of cooling right now, but the temperature is actually going up. A fun fact of the day. Common phrase in science. So you start to make these things, you start to correlate. And so a common phrase in science discussion is correlation does not equal causation. Correlation means a connection between two things. Causation means the action of causing something. So this is a true story. I went to Hawaii once. I was on a beach, and there was a woman there selling like little jewelry trinkets, and she came over and was like, which one do you want to buy? And I was like, I don't really want to buy anything. And she's like, well, you're surfing this one, and it's like this little, I still have it actually. It has like this like little metallic round circle-y thing. Looks like a little medallion. She's like, this one protects against shark attacks. And it was like $3. And I was like, sure, I'll buy it. And so I did, and I still have it. And I went surfing that day, and guess what? I never got eaten by a shark. True story. Is that what correlation is that? Correlations are measured as percent. That's a 100% correlation. In science, an 80% correlation is fantastic. 100% is like unreal. People think you're making up the results if you get 100%. But when I wore that medallion, I did not get eaten by a shark. Now, causation means, did that medallion actually prevent me from getting eaten by the shark? If you're thinking no, you're probably correct. Because that's like a really funny example. So how do we determine? Well, I'd have to get a Shark Tank, right? I'd have to get a medallion. Well, I wouldn't do it. I'd get like a lab assistant, right? And you'd be like, hold the medallion, jump into the Shark Tank. And then you just kind of see like what happens, right? And that's a very easy way of telling these. But correlating and figuring out the actual causation becomes sometimes very, very difficult to do. Such as one that's a little bit harder, but they've correlated that if you sleep more than 9 hours, you have a higher risk of heart attacks. So does sleeping an hour more per day lead to more like a weakened heart, to having more heart attacks? And that answer is probably not. The real causation is that if you're sleeping that much, that means you're probably not exercising as much. And that over then long terms, that just happens to be kind of like a warning red flag of like, hey, you're living too sedentary a lifestyle, that kind of thing. And then eventually over that kind of leads to maybe like, some heart issues. So this, they can start to become grayer, and you start finding some of these correlations. You're like, does this actually cause this? Or is this like step 4 on the 5-step path of some kind of process? So what does the phrase correlation does not equal causation? Is that even if we find things that correlate with each other, and they have 100% correlation, does not mean they cause each other. So let's go back to my graph real quick. Right? September Arctic sea ice decreasing matches with glaciers decreasing. Does one cause the other one? Probably not. I would expect probably not. So that becomes a little bit interesting. So even though things correlate, you need to figure out, do they work with each other? And then we start to go into if a phenomenon can have many meaningless relationships, how can you figure out the correct causation? And really, this is the good question of science. This is what science is. That you have to test things, and you have to retest them. And we do retest them over and over and over again to see like, hey, was that causation and correlation a fluke? Does it always happen? Does it happen in these circumstances? Like let's try to figure out why it kind of happens. Which then goes into number 6 of, if the idea, and this is true, that if nothing in science can be proven, it just can't. There's only evidence for and evidence against. So can you try to find some evidence for flat Earth? It would be difficult. It'd be very, very difficult. Let's say there is some like a tinge, or maybe someone's like anecdotal feelings on the subject, right? Which probably wouldn't even count anyways. But then there's a huge amount of evidence that being like, hey, that doesn't count. People will veer towards the one with more evidence. So it's like the blind scales of justice. It's very hard to prove one way or the other, but we just go which one does the evidence point towards, and that's just the best that sometimes we can do. So let's kind of go back up to my first one of what happened here. So this was a direct correlation. Carbon dioxide going up, temperature going up, and people are like, that's 1 and 1, that's pretty good. Until they got to here, like carbon dioxide is still going up and temperature is not going up as fast. What happened? And what we eventually figured out is this new one, the ocean heat. We talked about joules last time with specific heat and latent heat. And that water has a really good amount of ability to hold in heat. I call it heat capacity. Hold in heat before it changes a degree in temperature. And it can take in a whole bunch of heat before it goes up 1 degree. It can take in 4 joules. Think of how big the ocean is. Times that by 4 joules. That's the amount of heat that the ocean will have to absorb before it goes up 1 degree. So when we were originally measuring the ocean in temperature, just temperature, and we're like, hey, the ocean's still not changing, still the same temperature, we did not realize that the ocean was sucking in a whole amount of heat that it was just kind of hidden from us. We're like, oh, air temperature is kind of staying constant. Those gases are going up. It looks like everything's going to be okay. And you're like, no, not really. The ocean heat level is skyrocketing. And eventually, sooner or later, that will start to go up in degrees and temperatures as well. And we're starting to see that. But we kind of forgotten that 70% of our world is water. And that water can take in a whole bunch of heat before it goes up a degree in temperature. This is also going to be a big issue of it takes a long time for it to then go down a degree in temperature as well. So reducing global warming in the future will, I said, it won't happen for us. But it could happen for later generations, that this graph will extend for a long time before it eventually starts to work its way back on down. So that's pretty much what happened up here with this regard to global average temperature. Which then also brings up the question of, how can we talk about global warming events and how does it affect weather? And you don't really often see this, but they're like, can I really truly say that Category 5 hurricane that went through this past year was caused by global warming? And that answer is no. That's not the way it works. And then many meteorologists, have gotten some criticism about this. Like, why aren't you saying that, hey, this flooding is caused by global warming? Is because they can't. And the reason why is because we don't know. And a good, I think, metaphor for this one, or analogy, is what they call the popcorn analogy. Like a popcorn experiment with actual popcorn. You take a bag of popcorn, you put it in the microwave for a minute. You pull it out, you count the amount that pops, and you count the amount that does not. And there's a certain amount. We can make up any number that you like let's say 50% pops. You put it in the second bag, right? Same microwave. Instead of doing it for 1 minute of heat, you do it for 1 minute and 10, right? And as you would expect, more popcorn pops. And you can do that 100 times. You'll be like, okay, for 1 minute, it goes 50% pops. For 1 minute and 10 seconds, it goes 55% pops. Just a 5% increase. The problem is when you open those bags up and you take a look at all those popcorns on both of those bags, one that was 1 minute and one that was 1 minute and 5 seconds, right? How can you pull out one kernel and say, this is the kernel that popped because of that extra 5 seconds? You just can't. You don't know. And that's really the big issue, is that we know on average storms will increase, and they are. But how can we pick out one individual storm and be like, hey, this is the storm that was caused by global warming that we wouldn't have had normally? And that answer is that we just can't. So that is the big conundrum that meteorologists and some weather scientists and climatologists are in. They're like, we're getting more flooding. But but people are like, is this the flood that was caused by global warming? We're like, you can't tell for sure. We just had this massive snowstorm a few months ago, right? We got like 22 inches. The number 8th biggest, I think, snowstorm we've ever gotten. Was that one caused by global warming? We were like, well, we're supposed to get more extreme storms even during the winter. I don't know. And that's really the answer, is that we can't really tell one way or the other, which is like a contradiction of what people want us to do. And it's just how science works. So it doesn't always work sometimes out in the way that you kind of want. Because I think people would really respond better if they're like, this storm is caused by global warming. 100% for sure. And that answer is that can't ever happen. So that's just one of the things that we have to deal with. So hopefully you kind of got some stuff out of this sheet. This truly is those graphs. I'm not making any of these up. If you want to see even the more modern ones, I should probably update these. That's on the website. I'm sorry, I'm scrolling back and forth too much. Here it goes, climate.gov. A really interesting one. Has some really good stuff on it if you want to go take a look at that. Earth's Research Laboratory is another really cool website to actually kind of go through as well. The last thing I have for you to do is just like a little online form. We have finished our second week of online school. I'm just curious, how are you feeling? How are things going? Is it working out okay for you? Are things not going so okay? Feel free to write anything that you like. And the second question is there anything I can do to help you out? I know some teachers are doing like more Google Meets. I know some are not. I think I'm just going to do open office hours maybe like next week. So I'll just be on if you want to come on and chit chat. I think maybe I'll just even do like total non-school related chit chat hours, maybe like towards like the evening, like after my kid goes to bed. We can like I'll probably put on there as well. I'll do it on Twitch. You guys can watch me play a game as I do it. But if there's something I can do for you, let me know. I'm only limited by the ideas I can think of, but more brains are better than just one, as they say. So is this graded? No, this will not be graded. Climate activity, I'm more interested in you understanding what global warming is, how these graphs actually work, and maybe actually going to one of those websites and kind of reading a little bit about it. I think that will be much more beneficial to you than me just giving like a point or two like on this assignment. That simulation, pretty neat little thing. If you want to kind of go take a look at it, no questions to do. So feel free to take a look at that one as well. Besides that, this concludes at the end of our 2-week adventure. This video got long. Sorry, sometimes I get kind of rambling when I talk about global warming on occasion. So thank you for listening, and I'll see you next time. Bye, guys.